Okay, welcome back. In this video, I wanted to make a brief introduction into what are the basic statistical analysis concepts that we can use in order to understand information that we have from the environment, from a medical process, for testing a drug, to understanding the behavior of data coming from example from an engineering system, for example, an electric motor, a water network, and a structure, electrical circuit, no? And well, will be the first video from a series of video that I will be uploading to YouTube in order to, the main objective is that I present this information to a broader audience, no, from my point of view, no? But also I wanted to practice or remember some of these concepts a little bit. Also, I will be uploading some videos in which we can perform, for example, hypothesis testing or computer correlation analysis using Python. Okay, so there will be also videos related to this series of videos that will be focused on how we can use these software tools in order to perform this statistical analysis. So the main point of this series of videos is to focus on the aspect of inferential statistics. I will be discussing what is inferential statistics later on, but before I dive into inferential statistics, I wanted to first explain what is the main objective of statistics, no? And basically, statistics as a field focuses on studying the methodologies for collecting, organizing, and summarizing data. Okay. And also, we want to analyze that data in order to draw conclusions and make decisions. Okay. For example, if a doctor wants to know if a drug has a certain effect on patients or not, maybe he can run an experiment, no, make an experimental design, and afterwards he can collect data from that experimental design, and based on that experimental design, he can run a statistical test in order to see if the drug has certain effect on the population or, well, more than in the population, we will discuss that what is the meaning of population, but from the sample that he has collected from the population in order to see if the effect is having the expected effect or not from a statistical point of view. So, statistics can be divided into two main branches. We have descriptive statistics that is basically focused on summarizing data. And when you compute, for example, a mean and standard deviation, the median, of the courtesies of a population or a sample, well, basically what we're doing with that is to summarize the data. Also, you can use, for example, certain plots to summarize or understand the data, like computing the histogram, okay, of the variable that you want to study. Maybe you can use a scatter plot or use a bar plot in order to understand the behavior or the distribution of your data, okay? But here this video will be focused on inferential statistics. That doesn't mean that we'll not be using some tools from descriptive statistics because at the end they are interrelated. But from my point of view, the complicated part about the statistics is the inferential part. Okay, because at the end, this inferential part is the branch of statistics that can help us to make conclusions based on the data that we have from a population. Okay. And well, inferential statistics can help us to, for example, estimate models that describe the data that we have collected. This is also related to machine learning. Hypothesis testing that basically help us to see if there is an effect or a difference in a variable between different groups. And also we can, as I mentioned before, we can generate models that can help us to predict certain outcome in the future. Okay. For example, when you train a neural network or logistic regression to make a classification between two groups, well, basically what you're doing is to perform this inferential statistical approach of statistics. Okay, so before we start discussing what are the techniques of inferential statistics, I think that it is important that we first describe or understand what are the key concepts of any statistical analysis. First, we have the populations, okay? And the population is basically all the elements that belong to a set that share common characteristics. For example, a population can be all the students here in a classroom, okay? So that will be the population, no? All the elements that share common characteristics, no? And for example, the students in a classroom share the common characteristic that they belong to the same group, okay, at the same time. But in reality, it's quite complicated to gather information for all the population. Maybe you can say, okay, if the group is small, collecting the data from all the students is relatively simple. But imagine that you can expand this or expand the analysis to all the students in a university. Well, you will need to collect data. For example, you want to know what is the behavior of the heights or the weight of the students. Okay, what you can do is to make a survey and collect that information from every student. But the challenging part of making that is that, well, you need a lot of time and a lot of money, no? And a lot of resources at the end in order to collect the height and weight of all the students. So a better approach is to gather a subset or that whole universe. And that subset of that whole universe is what we call a sample. That will here I place the definition basically refers to a representative subset of the elements belonging to a population. Okay, this sample is selected via sampling procedure that allows the collected data to represent the population adequately. And well, this is an important point, okay, because collecting that sample, uh, from a resources point of view, it is better because you don't need to analyze all the individuals in the universe that, well, in the example that I was making before, we were talking about the students in a university and their weights and heights. But the challenging part of collecting the sample is that it needs to represent the population. How can we ensure that? Well, the base approach to do that is to collect that sample randomly. This helps us to reduce the bias because maybe the distribution or the behavior of the weights and heights, if I only sample from an individual group, no, or certain students, maybe the information that I collect will be biased to that group. Okay, so we need to avoid that, and the best way to avoid that is to collect a single random sample that considers or that all the students have the equal chance of being selected in this uh, sampling collection. Okay. And well, the term that I want to mention is what is the meaning of the variable? And the variable is basically the quantity that we want to analyze. That, for example, in the previous case that I was explaining to you, that I want to know what is the distribution or the behavior of the weights and heights in the students in a university. Well, these are my two variables. No? I want to understand the behavior of the weights and the behavior of the heights in the students at my particular university. Okay. And these variables could be qualitative and quantitative. In this case, with the weights and heights are quantitative variables because we can measure those. But for example, qualitative variables could be, for example, the gender of the students. They can be female or male. Okay, so we will be discussing later this idea of variable, sample, and so on. But the important thing that I want you to remember, the variable is essentially the thing that you want to study. Okay? It can be the temperature, it can be a pressure, it can be a force, it can be the energy of a system. No? If you want to use a statistic in an engineering setting, the dimensions of a mechanical design, no, the energy consumption of an electric circuit, no, the voltage and the current of in an electronic device. Okay, anything that we can measure and that we want to study. Okay, so well, this is basically a graphical explanation on what is the population and what is the sample. As I mentioned before, the sample is essentially a subset of the population that we have collected randomly. Okay, that is very important in order to avoid bias when selecting the data that we want to study. And why we're always analyzing samples and not the entire population, because it is cost effective, it is feasible, and we can reduce the time constraints, no? Or we can mitigate time constraints because we don't need to analyze the whole universe of persons or things that we want to study. Okay, so typically, when you have, let's say that we have already collected the data from the sample related to heights. So one way to analyze the data is to plot it using a histogram. The histogram is basically plotting along the x-axis the quantities of the values of my variable. Here I am plotting the formation of heights in centimeters, and I can use this histogram, no, that is very similar to a bar plot. The difference here is that we are uh, plotting the frequency of certain ranges of values in my variable. For example, here I am plotting the frequency of values between 160 and 170, and I can use the height of this histogram in order to denote what is the frequency, no, of my variable within this range. Okay, here from this histogram, we can notice that the range of values between 170 are higher compared to having a person with a height of 200 centimeters or below 140 centimeters. And this is useful because also we can place at the top of this histogram a probability density curve that is essentially a mathematical model that we can generate based on our data that describes the probability. Okay, we can compute probabilities of collecting a value of a certain variable from a sample of from taken from a population, and based on that compute the probabilities. Okay, it's basically a mathematical model that describes the behavior of my variable. Okay, and based on that we can also identify low probability and high probability regions. Okay, and this is relevant because sometimes we can make conclusions based on this. For example, we can say, okay, we can expect that if I collect a sample, no, from the heights of the students in my university, it is highly probable that the height is around 170 centimeters. Okay, so that's the whole point of making this analysis, no? That we can make an estimations, we can understand the behavior of the population by analyzing a particular variable. And uh, well, this is only an explanation of what is a distribution. The distribution is basically the behavior of the variable that I want to study. Okay, it's basically a function, no, or a description that tells us about how my variable is working, no? How my variable is behaving. And well, the histogram and the density curve are essentially distributions, no? And they basically show you the probabilities of how the probabilities of measurements are distributed. Here in this graph, we will notice that, okay, there is a higher probability, no, or there is a higher frequency of hits between 160 and 180, no, if we analyze this range. But outside these values, the probability or the frequency of those values gets lower, okay? But the advantage, as I mentioned before, of the probability curve is that well, we can compute probabilities based on the probability density curve compared to the histogram. Okay, the histogram is only a visualization tool. And well, depending on the behavior of the variable, and if the variable is continuous or discrete, you can have many types of distribution. Now you can have a uniform distribution, an exponential distribution, a normal distribution, a binomial, geometric, hyperbolic, and so on, that we can classify between continuous and discrete variables. And as you can see here, we can generate mathematical models or equations that describe the behavior of these probability distributions. Okay, and that is useful because based on those models, we can compute probabilities. Okay, we can make estimations. You don't need to worry too much about all these probabilities, at least for these videos. And after we introduce this idea of the central limit theorem, we will notice that one of the most important distributions that we care about is the normal distribution. That doesn't mean that the other distributions are not important. But typically, the statistical test that we'll be discussing here will require that in order for applying correctly that statistical test, we need to work with normally distributed data. Okay, that is a key assumption of many of the statistical tests and also some machine learning techniques that you can use to make classification or pattern recognition. One of them is the linear discriminant analysis, but at least you don't need to worry about all those ideas right now. The important factor is that we need to impose this condition. Okay, we need to understand that this is the condition that we uh, that many statistical tests imposes, and this makes the normal distribution quite important for many applications in data analysis and well, in data analysis and in statistics in general. And in fact, typically, we'll be discussing what is a standard normal distribution. What is a standard normal distribution? As you can see here, the normal distribution will have a mean and a standard deviation associated with it. But the standard normal distribution has the characteristic that the mean is equal to 0 and the standard deviation is equal to 1. And well, in fact, we can convert many variables into a standard normal distribution by subtracting the mean from the variable and dividing that by the standard deviation. And based on that, we can standardize the variable into a standard normal distribution. Okay. And we will be discussing this standard normal distribution later on. You don't need to worry too much about it right now. Um, but before that, well, here I am only showing you again a histogram of heights. Here you can see, only to make this idea of the histogram a little bit more clear. Here let's say that I collected the heights of a sample from the university students. And here I plot within ranges, for example, between 150 and 155. I've noticed that the frequency of those heights is around 4. The frequency is between 165 and 170 is around 7. But let's say that the sample size here was relatively small. If I increase the sample, I can see here that the histogram starts to look quite similar to a normal distribution in the sense that it starts to look symmetric. It is not perfectly symmetric, but if I increase the number of samples that I collected, I will notice that this variable will start behaving like a normal distribution. It starts to get symmetric and centered in a certain value. Okay. So, in fact, I make a video of a Python code that I made in Google Collaboratory. You don't need to worry at this point about the code, but the important factor is that I wanted to show you here that here I basically generating a random seed in order to make reproducible results. And I say, okay, I want to generate a sample, no, that follows a normal distribution. So I said that the mean height is 170 and the standard deviation is equal to 10. And I say, okay, I want to draw samples from a normal distribution. And the sample size or the number of samples that I will be getting from this normal distribution will be equal to 500. So I am using a function from NumPy. I will later explain what is NumPy here in these videos. But let's say that I am using this function only to uh, simulate the behavior of a normal distribution that will have a mean height equal to 170 and a standard deviation equal to 10. And the sample size is equal to 500. And I am using this code to first plot the histogram uh, of this variable named heights. That well, this variable heights is equal to taking these random samples from this normal distribution that I previously defined, and well, I can generate this type of plot. But you will see here in the video that as I increase the sample size, you will notice that this histogram will start to get more symmetric as I increase the sample size. And this is quite, well, you will see in the video that this behavior holds. But the important part here is that this is an interesting result because this means that as you increase the sample size, you will expect that the variable will have a normal distribution. Okay, so that's why many machine learning tools or many people say, okay, I want many data because after you increase the data, you can ensure that your data will have a behavior that is can be easily modeled from a mathematical point of view. So it has its convenience. The challenging part is that when you don't have access to many data and you have a constrained data set. And that is a topic of discussion. No? It's, some people think that, okay, I have many data is more challenging. And we can say that because, or maybe we can assume that because, mm, well, you need to process more information, okay? And maybe you need to clean more information. But that doesn't mean that analyzing a small data set is quite easy. In fact, sometimes you will notice that when you have a relatively small sample size, the distribution that you will be analyzing will not have this normal distribution behavior. And that is a nonsense because you don't can apply many of the statistical tests that has the statistical power. Okay, we will discuss later what is statistical power, but the estimations or the inference that you can make is closely related to the fact that maybe the variable that you want to study does not meet the assumptions that the powerful statistical tests require. Okay, so before I dip into that, uh, let's see all this video. Here you can see that I am essentially running this code multiple times. And here is the behavior of the histogram with 500 samples. Here I changed the value to 10. And here is what I was explaining previously, that the behavior of the histogram is quite strange, you know? But if I start increasing little by little the samples that I take from my population, you will start see that the distribution starts to look little by little more symmetric. Okay. Obviously, you can say, okay, it's a simulation, but in reality, many things or many variables tend to this behavior, but that depends mainly on the data that you can have access to. Okay. For example, here I increase the value to 2000. This is 5000. Okay, you can see that there starts to look very symmetric. You know? This is 10,000 values. And you can see that the values are centered around 170. That in fact is the mean height that we defined previously. Okay, when we were generating this randomly variable. Okay, so well, typically we can't um, compute the probabilities of a standard normal distribution using this formula. Okay, but well, that will be the topic of a later video. The important factor here is that this behavior of a normal distribution is quite essential. No, typically we want that all variables have this behavior because we can compute probabilities relatively simple using this expression. Okay, you don't need to worry about the integral because computing this integral analytically is quite challenging. So instead of doing that, we will be using a numerical approximation, but making a numerical integration or a numerical approximation of this integral requires using computational power, okay, or a computational software. And in this case, I will later upload a video in which I will show you or make some exercises in which we can compute probabilities from a normal distribution using Python, okay? So, well, this will be all for this video and see you later.